All right, welcome back. So today we are tackling a true legend in the world of coding problems, finding the first missing positive integer. It sounds so simple, but the solution? Oh, it's a total masterclass in thinking smart and efficiently. Let's just dive right in.
First up, let's set the scene. This thing looks super simple on the surface, but it's got these hidden rules that turn it into what feels like, well, an impossible puzzle. All right, so here's the actual job. You get an array of numbers, totally unsorted. Take this example. We have 3, 4, -1, and 1. The positive numbers in there are 1, 3, and 4. So the smallest positive one that's not in the list is 2. Seems simple, right? Yeah, not so fast. And here is the catch. There are 2 of them, actually, and they make this thing famous. First, your algorithm has to be fast. It has to run in what's called linear time, or O of n. Basically, you can only loop through the array a set number of times. But the real kicker, the thing that makes this so tough, is constraint number 2. You can only use a constant amount of extra memory, O of 1 space. You know, if that space rule didn't exist, this problem would be a piece of cake. You could just toss all the positive numbers into a hash set, loop from 1 up, and find the first one that isn't in your set. Easy. But that set uses O of n space, and that's a big no-no according to the rules. So we got to find another way in. Okay, so the solution, it's all about this hidden clue. It's about changing how we see the array itself. It's not just a box of numbers, it's a tool we can actually use. And this is the big aha moment. Think about it. What if we could get that amazing super fast lookup of a hash map, but without actually using a hash map, without using any extra memory at all? What if the array could do that job for us? This idea, it's called an in-place hash. The whole concept is to use the array's own bones, its indices, to keep track of the numbers we care about. And since we're looking for numbers like 1, 2, 3, and so on, this seems like it could actually work. Yeah, check this out. It lays out the mapping perfectly. So if we see the number 1, we can just do something to index 0. If we see the number 2, we mess with index 1. Basically, for any number x we find, its home base is index x minus 1. Right, but that brings up the next big problem, doesn't it? Like, if we use index 2 to say, hey, we saw the number 3, we can't just blow away the number that's already sitting at index 2. We might need that thing later on. So how do we leave a breadcrumb without burning down the forest?
The answer is this absolutely brilliant 3-step method. We're going to walk through the array 3 times, each time with a very specific job to do, and it solves the whole thing.
Okay, so first we clean house, get rid of all the junk we don't need. Then second, we do our marking. And finally, in a third pass, we just read our marks to find the answer. Simple as that. All right, step 1, the cleanup. Look, we only care about positive numbers that could actually fit in our array, right? So numbers from 1 up to n, the length of the array. Anything else, negatives, zeros, or huge numbers, is just noise. So we just walk through and replace all that junk with a safe number, something like n plus 1. Since n here is 4, that -1 just becomes a 5. It's out of range, so we can ignore it. Okay, now for step 2. This is the really clever part, the marking. We go through our now clean array, number by number. We see the number 3, so we jump to index 2, and we flip the sign of whatever's there. We see the 4, we jump to index 3 and make that number negative. See the 1, we jump to index 0 and flip its sign. And here's a key detail. We always use the absolute value of the number to find the index. That's so we don't get messed up if a number we're looking at has already been turned negative. And finally, step 3, the big reveal. We just walk through our modified array one last time, and we're just looking for the first spot that's still positive. So index 0, it's negative. That means we saw the number 1. Index 2 is negative. We saw 3. Index 3 is negative. We saw 4. But wait, look at index 1. It's still positive. That's our smoke signal. It's telling us we never ever encountered the number 2. So the answer is the index, which is 1 plus 1, and that's 2. Okay, but a great algorithm has to handle the weird stuff, right? So let's throw some curveballs at this method and see if it breaks. So what about duplicates? Say we have 1, 1, 1. Our marking step will see the first one and flip index 0 negative. Then it'll see the other ones and try to do it again. But that's totally fine. Because we use the absolute value, it just stays negative. So when we scan for the answer, we see index 0 is negative, but index 1 is positive. So the answer is index 1 plus 1, which is 2. Correct. Okay, what if there's a 0 in there? No problem. Our cleanup step was made for this. With an array like 1, 2, 0, that 0 is just junk. It gets replaced with n plus 1, which is 4. Then, we mark that we've seen 1 and 2, which turns indices 0 and 1 negative. The first positive number we find in our final scan is at index 2, so the answer is 3. Works perfect.
All right, last one. What if nothing is missing? Let's say the array is 1, 2, 3. Well, our marking step is going to see the 1, the 2, and the 3, and it's going to flip the signs at indices 0, 1, and 2. The whole array becomes negative. So when we do our final check, we find no positive numbers at all. What then? Simple. If everything is accounted for, the next missing one must be n plus 1. In this case, that's 4. Flawless.
Okay, let's just step back for a second and appreciate how cool this is. This is what people mean when they talk about in-place genius.
I mean, the real magic trick here is that O of one space complexity. We didn't build any new lists, no hash maps, no extra data structures at all. Everything we did happened right inside the original array. We just manipulated it in this really clever way.
You know, the only reason this whole thing even works is because of a math idea called the pigeonhole principle. It basically says that if you have an array with n spots, the first positive integer you're missing has to be somewhere between 1 and n plus 1. There's just no other possibility. And that's why we can safely ignore all those other numbers.
So, if you remember anything from all this, let it be these 3 core ideas. First, the wild idea of using an array's own indices as a kind of built-in hash map. Second, that slick trick of using the negative sign as a scene flag without actually destroying the number itself. And third, the fact that you can pull off this whole complex dance with just 3 simple walks through the array. That's what gets you to O of n time. And that kind of leaves us with one last question to chew on. This whole technique, turning an array against itself to store data, it's unbelievably powerful. So you have to wonder, what other problems out there that seem impossible could be cracked wide open with this same kind of thinking? Thanks for joining me.